This example will deal with angular motion, in which we will try to calculate the angular acceleration of our rotating object. So let's suppose that a massless rope, shown here, attached to a box that has a mass of 2.04 kilograms. And the rope is attached, it's wrapped around a pulley that has a frictional torque of 5 newtons times meter. So inside that pulley we have a frictional force that creates a torque that points in the clockwise direction. Now, if the box creates a force of 20 newtons due to the gravitational pull of the earth, we want to calculate the angular acceleration of our pulley. So when this box is being pulled down by the gravitational force, this object, our pulley, is rotating, and we want to calculate the angular acceleration of its rotation. So let's begin by making this assumption that our moment of inertia is 0.9 kilograms times meter squared. So we calculated this value in the previous example. So let's begin by recalling the equation for our sum of torques. So the net torque acting on the object is simply the sum of all the torques that our object has. So the object has two torques. One torque points in the counterclockwise positive direction, and that's the torque created by the tension in the rope. And the second torque is created by the frictional force, and it opposes our counterclockwise rotation. So our frictional torque points in the clockwise direction, so that means it has a negative sign. So we have the sum of all the torques acting on the object that is rotating is equal to our positive torque, torque tension, minus our torque due to the frictional force. Now this is equal to our moment of inertia of the object multiplied by our angular acceleration. So let's replace this torque tension with our force tension that is acting perpendicular to the lever arm. And the lever arm R is simply our distance, 50 centimeters. So we find that the product of the moment of inertia and the angular acceleration is equal to force tension multiplied by the lever arm, the radius of the pulley, minus our frictional torque. So this is the equation for angular motion that we will use in the end to calculate what our angular acceleration is. So this is the equation for angular motion. What about the equation for linear motion? So our box is moving in the vertical direction. So when the box is traveling vertically downward, it's rotating our object. So let's calculate all the forces, the net force acting on our object. So the sum of all the forces acting on the object is equal to, well, we have two forces acting on the object. We have the force due to gravity, M times G, and we have force in our rope, so the tension in the rope. So we choose going downward to be positive, going upward to be negative. So we have the sum of all the forces is equal to the gravitational force minus the tension in our rope, Ft, is equal to, well, this box is accelerating with some linear acceleration. So that equals m times a, where m is the mass of the box. So let's replace Fg with m times g minus Ft equals ma, and let's rearrange the equation and solve for the tension in our rope, Ft. So we see that Ft is equal to m times g minus m times a. Now notice in this case, the linear acceleration of the box is exactly the same as the tangential acceleration of our rope at this point. So that means our A tangential is equal to our A linear acceleration. And recall that A tangential is equal to the product of the radius, the lever arm, and our angular acceleration. So now we can take this quantity and substitute it into this equation. So we substitute equation 3 into equation 2. So we get the following result. The force tension is equal to m times g minus m times our alpha times our lever arm. So let's label this as equation 4, and by the way, we label this equation as equation 1. So now we take equation 1 and we substitute this quantity into equation 1. So we substitute equation 4 into equation 1. We plug this quantity into the force tension in equation 1. And we get the following result. Well, we have our moment of inertia multiplied by our angular acceleration is equal to, we have this entire quantity being replaced into this value, so mg minus m alpha times our lever arm multiplied by the lever arm minus the torque due to the friction. So let's multiply the r out and we get our mgr minus m alpha r squared minus torque friction. So now we bring all the alphas, all the angular acceleration to the left and everything else to the right. So we get the following result. So we have the moment of inertia multiplied by alpha, our angular acceleration, plus our mass times alpha times our lever arm squared, our radius squared, equals mgr minus torque friction. So now we take out the alpha and we have alpha multiplied by I plus mr squared, and we bring the alpha plus mr squared to the right side. So we get the following equation, and now notice we have the following value. So the numerator is simply our net torque and our denominator is the total moment of inertia of our object. So we know what I is, it's 0.9 kilograms times meters squared. We know what m is, it's 2.04 kilograms. We know what r is, it's 0.5 meters, so we simply convert centimeters to meters, divide that value by 100. So we know what g is, it's our constant 9.8 meters per second squared, and we're given what the torque friction is. It's 5.0 newtons times meter. So we plug those values in, and we plug that into the calculator, and we get that our angular acceleration of the object is 3.55 radians per second squared. So as this box is moving downward, vertically downward, it's rotating our pulley with an angular acceleration of 3.55 radians per second squared.